Okay, we are going to move on now to testing a proportion P, which is section 8.3. The focus points for this section are to identify the components needed for testing a proportion, compute the sample test statistic, and find the p-value and conclude the test. You guys can go ahead and read that. The key point here is to realize here that we have p hat again, which is r, the success, divided by n, the number of trials. Feel free to pause at any point to take any extra notes you would like to take down. The letter Q again is representing the probability of failure, so Q equals 1 minus P. Remember that for large samples, we're going to do N times P greater than 5 and N times Q greater than 5 in order to figure out if we can use this. And then mu is equal to P and sigma is equal to the square root of P times Q divided by N. All right, the null and alternate hypotheses for the test of proportions are the following. So P is going to be equal to K, or P is going to be less than K. P is going to be equal to K, or P is going to be greater than K, or P is going to be equal to K, or P is not going to be equal to K. Depending on what is asked for the problem, notice that P is probability and K must be between 0 and 1. Okay. I would definitely recommend taking notes on this slide. For a test of proportions, we need to convert the sample test statistic p hat to a z value. Then we can find a p-value appropriate for the test. The p-hat distribution is approximately normal with mean p and standard deviation given as the square root of pq divided by n. Therefore, the conversion of p-hat to z follows the formula. So go ahead and pause the video so you can take that down or retake it down. The more you write this stuff, the better you will be. Using this mathematical information about the sampling distribution for p-hat, the basic procedure is similar to the test you have conducted before. All right, again, in your own words or shorthand, write the requirements down. This is the procedure on how to test a proportion P. And here's the actual procedure. In example 6, for testing P, a team of eye surgeons has developed a new technique for a risky eye operation to restore the sight of people blinded from a certain disease. Under the old method, it is known that only 30% of the patients who undergo this operation recover their eyesight. Suppose that surgeons in various hospitals performed a total of 225 operations using the new method and that 88 have been successful, as in the patients fully recovered their sight. Can we just claim that the new method is better than the old one? Use a 1% level of significance. So that means your alpha is going to be equal to what? Yes, it would be 0.01. First, you need to establish your null and alternate hypotheses and note the level of significance. So the level of significance here is alpha equal to 0.01, like we just said. Let P be the probability that a patient fully recovers his or her eyesight, and the null hypothesis is that P is still 0.30 even for the new method. The alternate hypothesis is that the new method has improved the chances of patient recovering his or her eyesight. Therefore, the null hypothesis is P equal to 0.30 and the alternate is P greater than 0.30. Okay, again, notice they did not make up their own values. They took it directly from what they were given. Check requirements. Is the sample sufficiently large to justify the normal distribution for p hat? find the sample statistic and p hat and convert it to a z value if appropriate. I apologize for that slide. Obviously, there were some issues when they made it. Using p from h sub 0, we note that n times p is 225 times 0.3, which is 67.5, which is greater than 5. And then 225 times 0.7 will give you 157.5, which is also greater than 5. So we can use the normal distribution for the statistic p hat. Again, it's kind of messed up. So p hat is equal to r divided by n, which is 88 divided by 225, which is 0.39. The z value corresponding to p hat is given as follows. They just plugged everything in and found 2.95. In the formula, the value for p is from the null hypothesis. Okay, so you can find Q. Find the p-value of the test statistic. Figure 810 shows the p-value. Since we have a right-tailed test, the p-value is the area to the right of z equals 2.95. Okay, and you can see that there. Okay. Again, I would definitely get in the habit of drawing these diagrams. Using the normal distribution, you can look at table 5 of appendix 2. We find the value equal to the p-value where z is greater than 2.95 to be 0.0016. Concluding the text, since the p-value is 0.0016, it is less than or equal to 0.01 for alpha, so we reject the null hypothesis. Interpreting the results in the context of the problem. At the 1% level of significance, the evidence shows that the population probability of success for the new surgery technique is higher than the old technique. Okay. Okay, we're going to move on to section 8.4. Test involving paired differences dependent samples. Identify paired data and dependent samples. Explain the advantages of paired data test, compute differences and the sample test statistic, estimate the p-value, and conclude the test. Paired data. Many statistical applications use paired data samples to draw conclusions about the differences between two population means. If you guys want, you can try and think about paired data that you've seen examples of in the past. That could be pretty cool. I think I mentioned to you guys before that there was a twin study that was not published and extremely controversial, done, I believe, in like the 60s and 70s in New York and the New Jersey area. Super, super controversial. You know, people on both sides, one saying, you know, that it was scientific and good for research, but yet it was never published, mainly because I don't think they really came to any conclusions, and it just was really unethical with what they did. And if you guys would like more information on that, I can direct you to the documentary that I watched about it. It was very disheartening for sure. So data pairs often occur naturally in a before and after situation where the same object or item is measured both before and after a treatment. Applied problems in social science, natural science, and business administration frequently involve a study of matching pairs. Psychological studies of identical twins, biological studies of plant growth on plots of land matched for soil type, moisture, and sun exposure, and business studies on scales of matched inventories are examples of paired data studies. When working with paired data, it is very important to have a definite and uniform method of creating data pairs that clearly utilizes a natural matching for characteristics. Okay, the next example and guided exercise demonstrate this feature. So we're looking at paired data for example 8. A shoe manufacturer claims that among the general population of adults in the United States, the average length of the left foot is longer than the right. Now I'm definitely going to have to pay attention to my feet when I get home. To compare the average length of the left foot with that of the right, we take a random sample of 15 US adults and measure the length of the left foot and the length of the right foot for each person in the sample. Is there a natural way of pairing the measurements? How many pairs will we have? In this case, we can see each left foot measurement with the same person's right foot measurement. The person serves as a matching link between the two distributions. We will have 15 pairs of measurements. I guess unless they wanted the left feet of amputees, but then they wouldn't be able to match it with anybody unless they match them up with the right foot of other amputees. Morbid, a little bit scary. All right. When we wish to compare the means of two samples, the first item to be determined is whether or not there is a natural pairing between the data in the two samples. Again, data pairs are created from before and after situations or from matching data by using studies of the same object or by a process of taking measurements of closely matched items. When testing paired data, we take the difference D of the data pairs first and look at the mean difference D bar. Then we use a test on D bar. So Theorem 8.1 provides the basis for our work with paired data. Theorem 8.1 says consider a random sample of n data pairs. Suppose the difference D between the first and second members of each data pair are approximately normally distributed with population mean mu sub D, then the t values are given as follows. Where D bar is the sample mean of the D values and is the number of pairs, and S sub D is given as follows. Again, remember guys, you can use technology, you can use calculators, you can use Excel spreadsheet, you can use Google Sheet, but make sure if you're using something separate, you need to send it to me as part of your exam work. All right. And also remember that with degrees of freedom, we're going to do n minus 1. When testing the mean of the differences of paired data values, the null hypothesis is that there is no difference among the pairs. That is, the mean of the differences mu sub D is 0. So then the hypothesis for the null will be mu sub D equals 0. The alternate hypotheses depend on the problem and can be any of the three. For paired difference test, we make our decision regarding H sub 0 according to the evidence of the sample mean D bar of the differences of measurement. By Theorem 8.1, convert the sample test statistic D bar to a t-value using the formula. To find the p-value or any interval containing the p-value corresponding to the test statistic t computed from D bar, we use the student's distribution table, table 6 in appendix 2. We have found the test statistic t, or if t is negative, absolute value of t, in the row headed by the degrees of freedom n minus 1, where n is the number of data pairs. So in this case, you would take 15 minus 1, which is 14. The p-value for the test statistic is the column entry in the one-tailed area row for one-tailed test, right or left. For two-tailed test, the p-value is the column entry in the two-tail area row. Usually the exact test statistic t is not in the table, so we obtain an interval that contains the p-value using the adjacent entries in the table. Table 8.7 gives the basic structure for the student's t-distribution table to find the p-value or any interval containing the p-value. Okay. Again, I would recommend just going straight to the table. Procedure. how to test paired differences using the student's t-distribution. Go ahead and write your shorthand for your requirements and start writing your procedure. I'll give you a few seconds before I move on to the next slide. I know some of this might seem repetitive, but it's just going to get really hard if you don't write everything out and be super, super organized and detailed. I totally recommend having either index cards, highlighter, something so that you can help keep this stuff straight in your head. All right, example 9, paired difference test. A team of heart surgeons at St. Anne's Hospital knows that many patients who undergo corrective heart surgery have a dangerous buildup of anxiety before their scheduled operations. The staff psychiatrist at the hospital has started a new counseling program intended to reduce this anxiety. A test of anxiety is given to patients who know they must undergo heart surgery. Then each patient participates in a series of counseling sessions with the staff psychiatrist. At the end of the counseling sessions, each patient is retested to determine anxiety level. Table 8 indicates the results for a random sample of 9 patients. Score before counseling and score after counseling and difference. Okay. I don't know why they gave us the patient's names. Honestly, if you were filling this out, you should just use patient 1, patient 2, etc., or ABC or XYZ, whatever. You should not be giving out even just a person's first name. Okay. Higher scores mean higher levels of anxiety. Assume the distribution of differences is mound-shaped and symmetric. From the given data, can we conclude that the counseling sessions reduced anxiety? Use a 0.01 level of significance. Remember, that's your alpha. Before we answer this question, let us notice 2 important points. 1, we have a random sample of 9 patients, and 2, we have a pair of measurements taken on the same patient before and after counseling sessions. In our problem, the sample size n equals 9 is pairs of patients, and the d values are found in the 4th column of table 888. Note that the level of significance set and the hypotheses in this problem statement alpha equals 0.01, we want to test the claim that the counseling sessions reduce anxiety. This means that the anxiety level before counseling is expected to be higher than the anxiety level after counseling. In symbols, D is equal to B minus A should tend to be positive, and the population mean of the differences mu of D also should be positive. Therefore, we have hypothesis, null hypothesis equal mu sub D equals 0, and alternate hypothesis is mu sub D greater than 0. Okay. Check requirements. So the first thing you want to do is, we already know that our degrees of freedom will be n minus 1 or 9 minus 1, which is 8. The sample statistic D bar and convert it to a corresponding test statistic T. We first need to compute D bar and SD, S sub D, using formulas or a calculator, and the D values shown in table 8.8. We find that D bar is equal to approximately 33.33, and S sub D is equal to 22.92. Again, however you choose to find it is completely up to you at this point, because you have been tested on it already. But if you're using technology, please either send me the file or a screenshot or something to show me that you didn't just, pull it from somewhere, that you actually put in the effort. Using these values together with n equal 9 and mu sub D equals 0, we have the following t statistic of 4.363. Getting super tongue-tied right now. Find the p-value for the test statistic and sketch the p-value on the t-distribution. Since we have a right-tailed test, the p-value is the area to the right of t equal to 4.363 as shown in figure 813. And there it is. Okay. In table 6 of appendix 2, we find the interval containing the p-value. Use entries from the row headed by degrees of freedom equal to 8. The test statistic t is 4.363, falls between 3.355 and 5.041. Wow. Yes, I am so terrible at reading today. The p-value of the sample t falls between the corresponding one-tail areas 0.005 and 0.0005. See table 8-9 excerpt of table 6 appendix 2 if you can't follow that. There you go. Conclude the test. Since the interval containing the p-value lies to the left of 0.01, we reject the null hypothesis. Note, using the raw data in software, the p-value is roughly 0.0012. Interpret the results in the context of the application. At the 1% level of significance, we conclude that the counseling sessions reduce the average anxiety level of patients about to undergo corrective heart surgery. All right,